Welcome student. I am going to give a brief explanation for this week content in our Google Classroom for F2 section. I have uploaded one video under Classroom PPT unit wise for this week content. So I am going to give a brief explanation for this week content. This week we are going to discuss about only these three topics. What is virtual memory? What is virtual address space? What is demand paging? Under demand paging we are going to discuss about what is lazy swapper, what is the structure of page table, and the way of handling page faults, performance of demand paging. I'm not going to explain in detail about all these three things. I'm going to just explain a brief about this content. What is virtual memory? Virtual memory is the separation of user logical memory from the physical memory. Only a part of program will be loaded in memory, remaining will be available in secondary storage. So the virtual memory size will be bigger than the actual memory. So we are able to, programmer can assume a bigger size memory without worrying about the actual size of the memory. What is virtual address space? Virtual address space is the logical view of how process is stored in the memory. We are going to implement the virtual memory using a two-way demand paging and demand segmentation. What is demand paging? Loading the page only as they needed. That is demand paging. Simply speaking, demand paging is the combination of paging and lazy swapping. Paging plus swapping is called demand paging, but it's not an ordinary swapping, it's a lazy swapping. What do you mean by lazy swapper? It swaps the page from hard disk to the main memory, only the page is needed. That is lazy. When it is needed, the page will be swapped in, otherwise it won't swap. That's why it is called. So paging plus lazy swapping is called demand paging. And this is the way of swapping and swap out from the physical memory to the main memory. Okay. And the page table will contain one bit called valid bit, invalid bit. Suppose the page is available in the memory, the valid bit will be mentioned as V. If it is I, means the page is not available in the memory. So this page table clearly explains whether the page is available in the memory or not. Okay. I directly move on to the concept of page fault. Whenever a page is referred by a process, if the page is not available in the memory, that is page fault. How to handle the page fault? There are 6 steps. I will explain with the diagram. Here you see, when a process needs or referred a page, it refers the page table. Suppose the page table, the reference bit is I. I means invalid. If it is V, it will get the data from the frame. Suppose this diagram is only for page fault, handling page fault. So when a process refers a page, it check with the page table. Page table, the reference bit is I. Immediately a trap interrupt signal given to the operating system. Operating system initiate the disk scheduling disk controller to transfer the data from the disk to main memory. So after the data has been transferred from or swapped into the main memory, an instruction will be given to the page table. The page table will be updated with the valid bit. After that, the process will be restarted. Okay, these are the 5 steps of handling page fault. Okay, performance of a page. Demand paging. What do you mean by demand paging? Loading the page when it is needed. So what is the performance of demand paging? There are some measurements to find out the performance of a demand paging. 3 major activities involved in demand paging. One is service the interrupt. When the trap is given to the operating system, servicing the trap, identifying whether the trap is a page fault trap or some other part. So it will take very less time. And the third step, restart the process. Restarting the process also takes less time. But read the page from secondary storage to main memory takes lot of time. Okay, these are the, so the page fault is the major issue. Demand paging or the performance of demand paging directly proportional to the page fault. Directly proportional to the page fault. So page fault is represented as P lies between 0 to 1. P is 0 means there is no page fault. P is 1 means all the pages are page fault. That's the meaning of P lesser than or P lies between 0 and 1. Okay. Now the performance of demand paging will be measured with one formula called EAT, effective access time. Effective access time. Before that, I will tell you the meaning of other terms. MAT, memory access time. This memory access time, so the memory access time is the time taken by the memory, the data from memory to the process, memory access time. P means the probability of page fault. PGFT, I have given a meaningful term, PGFT, page fault time. So the page fault processing time or response time, that is PGFT. EAT, effective access time. So the effective access time of a data or page, the total access time will be the sum of the page fault access time, plus the memory access time. So how many page faults we have? P page faults are there. Sorry. So P page faults are there. P into the page fault access time plus 1 minus P into memory access time. So this is the first box is the time taken to process the page faults. The second part is the time taken to process the data in the memory. Okay. Sometimes the page fault can be classified into two: replaced page and modified. Sometimes we call it as a dirty bit. Dirty bit means the referred or replaced page will be modified. So the replaced page will be modified. That is called a dirty bit. So if replaced page is modified, then the P value will be of two types. Replaced page is modified, replaced page is not modified. So the EAT, effective access time, formula will be modified like this: PM into page fault time of page modified plus page fault time of page not modified. So these two values are together combined as P into PGFT. So plus 1 minus P into memory access time. The second time is same. In case if we have a cache memory, then the effective access time formula will be slightly modified. Cache hit into cache access time, cache miss into other access time. The cache miss into other access time will be the memory access time. P means it will be a virtual memory access time into the page fault time for that virtual memory plus 1 minus P, that is memory access time into number of memory access. 1 minus P, number of memory access, P, number of virtual memory access. So here cache hit into cache access time plus cache miss into these whole terms. Before we proceed to the problems, 1 second is equal to 10 power 3 microsecond. 10 power 3 microsecond equal 10 power 1 microsecond equal 10 power 6 nanosecond. 1 microsecond equal 10 power 3 microsecond. Millisecond, sorry, ms means millisecond. So second is greater than, millisecond is greater than, microsecond is greater than nanosecond. So between each and every terms the difference is 10 power 3, 1000. Means 1000 nanosecond is 1 microsecond. 1000 microsecond is equal to 1 millisecond. 1000 millisecond is equal to 1 second. So using this units, we are going to see some problems. Sometimes some data will be given in nanosecond, some data will be given in microsecond. So you have to convert from one form to another. Now we'll see some problems. Demand paging problem. Let the page fault service time be 10 microsecond in a computer with the average access time being 20 nanosecond. Here you see page fault service time, PGFT, page fault service time is 10 millisecond. But average memory access time they have given in nanosecond. So we have to convert the millisecond into nanosecond by multiplying 10 power 6. If one page fault is generated for every 10 power 6 memory accesses, so page fault is 1 by 10 power 6. What is the effective access time? See the solution. The given value, memory access time 10 nanosecond, page fault service time. Page fault service time or page fault time. Page fault service time is 10 millisecond. The page fault is 1 by 10 power 6. See the problem? If one of the page is generated for every 10 power 6 means 1 by 10 power 6. So effective access time is equal to the formula P into PGFT plus 1 minus P into memory access time. So if you fill up this value, we'll get 30 minus 2 divided by 10,000, 1 lakhs. It comes approximately 30 nanosecond or 29.00000, 29.9999.5, like that it will come, approximately 30 nanosecond. Here you see P into PGFT 1 by 10 power 6 into 10. Page fault access time is 10 only, but the 10 is given in millisecond, so we have to convert into nanosecond. So we have multiplied by 10 power 6. Okay. Now we move on to the second problem. In a demand paging memory system, page table is held in registers. The time taken to service the page fault is 8 millisecond if an empty frame is available or if the replaced page is not modified. This is second category. Modify, not modified in that category. Modify, not modified. So it's not modified. And it takes 20 millisecond if the page is modified. So this is the page fault time. Page fault time for modified page 20. Page fault time for not modified page 8 millisecond. What is the average access time to service page fault assuming that the page to be replaced is modified 75% of the time? So the modified pages are 70%, not modified percentage remaining 30%. Okay. Now see, given PM is 70%, that is 0.7. P not modified, page modified is 0.7, page not modified is 30%, 0.3. Page fault time of page modified is 20 millisecond. Page fault time of page not modified is 8 millisecond. Average access time to service the page fault. In this problem, we are not going to find out effective access time. We are going to find out only the service time for page fault. Okay. So in the formula, I will show you the formula. Here you see the formula. In EAT, there are two terms. The first term is the P into PGFT is the page fault access time. The second one is memory access time. Page fault access time, memory access time. In our second problem, we are going to find out only the first part. The formula will be the second one. Here, this second one, the first part only we are going to calculate, not the second part. That is 1 minus P into MAT we are not going to calculate. We are not calculating EAT. The second problem we are not going to EAT. We are calculating only the memory access time to service fault. So that is PM into PGFT into FPM plus P not M, page not modified into the page fault of page not modified. So PM, page modified 0.7. The page fault time of PM 20 millisecond. And then P not, page not modified 0.3. Page fault time of page not modified 8 millisecond. Now we no need to convert anything. Here I will give the value in my millisecond itself. So 0.7 into 20 is 14, 0.3 into 8 is 2.4. Totally the answer is 16.4 average access time to service a page fault alone. Third problem. In a demand based system, it takes 100 nanosecond to access memory. Memory access time. This is 100 is memory access time. Okay, they have given memory access time. Page table has 8 entries. and is held in register. It takes 10 milliseconds to service a page fault if the empty frame is available or if the victim frame is not dirty. So dirty bit, modified, not modified. So the service time, page fault time for not modified is 10 milliseconds. If the victim frame is dirty, modified, the page fault service is 20 milliseconds. Means the page fault time for modified is 20 milliseconds, not modified is 10 milliseconds. Assuming that victim frame is dirty 80% down. So the page modified is 80%, 0.8. Page not modified, remaining 20%, 0.2. Find the maximum page fault rate. Here the problem is they are asking P, value of P, for which the effective memory access time remains within 200 nanoseconds. They have given memory access, effective access time. The total effective access time they have given 200. They have, you see this solution. The value given are effective access time 200 and the page modified rate is 0.8, page not modified rate is 0.2. Page fault time for page modified is 20 millisecond. Page fault time for page not modified is 10 millisecond. Memory access is 100 nanosecond. That's very important. Memory access time is 100 nanosecond. Effective access time is 200 nanosecond. Remaining page fault time is given in millisecond. We have to convert into nanosecond by multiplying 10 power 6. Average access time to service page fault. First we calculate the page fault time, then memory access time we will add along to find out EAT. EAT is given, we have to find out P. So average memory fault access time, it is very similar to the previous problem. So 0.8 into 20, since it is given in millisecond, we multiply by 10 power 6 plus 0.2 into 10 and 10 power 6. So we multiply the 10 millisecond into nanosecond. Now from these both the terms, take 10 power 6 outside, the remaining values are 16 plus 2, 18 into 10 power 6. Now the formula EAT equal to P into PGFT plus 1 minus P into MAT, memory access time. They have given 200, EAT equal to P into 18 into this one we already calculated in the above, average access time to service the page fault. So P into 18 into 10 power 6 plus 1 minus P into memory access time they have given in the problem itself, 100. So if you 200 is there, 200 equal to from these two terms we take 100 outside, then P into 18 into 10 power 4. Instead of 10 power 6 we have taken 100 outside, so 10 power 4 plus in this term we have taken 100, so the remaining is 1 minus P. Now that 200 will go that side, so that side 200 by 100 is 2 equal to P into 18 into 10 power 4 plus 1 minus P. Now this plus 1 will be go to that side, so that side, the left side will be become 1, and then on the right side we take P common outside, so that will be 18 into 10 power 4 minus 1 into P. Now P is 1 by 18 0,000 minus 1, that is 1 by 179999. So that is approximately 5.55 into 10 power minus 6. If you want to mention in percentage, so 5.55 into 10 power minus 4 percentage. Okay. So we have seen many problems, 3 problems in this demand paging concept. Just I have given explanation more about this problem only. We discuss what is demand paging, what is virtual memory. Virtual memory actually is a form of RAM. Sometimes the demand paging page fault is of 2 types, replaced page. So when we replace the pages, that is sometimes called a global replacement process. And the formula for effective access time will be slightly modified if we use cache memory. So I forgot to show that formula. I'll show you. You see here, in case if you use cache memory, already I told, I think. So for this case, In cache memory, actually cache memory holds the recently referred pages. So the referred page, any process needs a page, it first refer the translation look aside buffer that is available in cache memory. The cache memory holds the recently referred pages. If it is not there, then it will refer either in the secondary memory or either in the memory. Memory means main memory, or if it is not there in main memory, that is page fault. Okay. I hope you enjoy this particular video helps you to answer for your weekly quizzes. Thank you. We'll meet once again in some other video.